Today we're going to start talking about the forces of attraction between molecules. These forces of attraction give a lot of different substances their physical properties, so it's a good transition from bonding, which are forces of attraction but between atoms, and the forces of attraction we're going to be talking about today are actually between molecules. To define that to start with, we're going to put forces that hold molecules together. These are the attractive forces that keep molecules near each other in solids, which are very strong forces, or liquids that are slightly less strong, and in gases, which are nearly non-existent. So since I said molecules, recall that we're talking about covalently bonded substances. So the things we're going to be talking about, save for one of these forces of attraction, don't involve anything but molecules. The first one we're going to talk about is dipole attraction, and dipole attraction occurs in polar molecules. These molecules, because they are polar, have a kind of positive end and a kind of negative end, like you see in these depictions here. So one end's kind of positive, one end's kind of negative, and because of that slight charge across the molecule, they can actually line up with opposite charges near each other. Examples of different substances where you might see dipole attraction would occur in any polar molecules. So we're just going to list a couple here. HBr, because the H end of the molecule is slightly positive, the Br end being slightly negative. Another one might be NH3, but we're going to talk about that one again because it gets a little more complicated with ammonia. When we talk about these dipole attractions, you can actually compare between different polar molecules how strong that attraction is. So if we look at the two examples we have over here, we have some larger molecules and then some smaller molecules. So that force of attraction between those molecules is different, and it's different based on size. So the larger they are, the greater that force of attraction, and I'm talking about between the molecules here. So if we were to look at a whole bunch of different molecules made from elements in the same group, so what we have in this list here are HF, HCl, HBr, HI. So H is the same in all of them, and all I did was I took elements from the same group or family, this being the smallest one all the way down through the largest one there. And what happens to dipole attraction within the group is that it will increase. So it'll actually increase down the group. And that's because of the size. Now we're going to talk about HF again shortly. HF is kind of special, kind of like ammonia is kind of special. And actually we're going to talk about it next when we talk about another type of intermolecular force. So these are forces between molecules or covalently bonded substances. Hydrogen bonding is the one you're most likely to see on the exam. It's the most important. It's also very, very strong. And this is due to a highly electronegative element bonded to hydrogen. So of course, our highest electronegative element, which is fluorine, is going to be included in this list. Also oxygen and nitrogen. Some people like to say hydrogen bonding is fun, F-O-N instead of F-U-N. So the different things that you're going to have to memorize then, the different molecules that do this are HF, H2O, and NH3. So that's hydrofluoric acid, water, and ammonia. Those are the only three molecules that you're going to need to know for the Regents exam. So let me show you what hydrogen bonding looks like. So these are supposed to represent water molecules. The yellow ones are oxygen and the green ones are hydrogen. So if you recall when we talked about bonding, the oxygen is going to have a much higher electronegativity, so the electrons are going to spend more time with oxygen than they do with hydrogen. And because hydrogen then consists only of a proton, that proton's really exposed on the outside of the molecule, giving this end of our molecule a slight positive charge, well, in this case, rather positive charge, and this end being really negative. There's no other shells of electrons in a hydrogen atom in order to kind of protect the nucleus from its charge being exposed. So as a result, anything that is bonded with hydrogen, like an HF and NH3 in the example we're talking with water, you're going to get an incredibly polar molecule. So all of these atoms are going to have the same thing going on within the molecule. As a result, these charges are really kind of strong, and they're actually going to attract the other atoms to them. So you're going to have all these forces of attraction going on between these atoms, and it's going to create kind of a lattice network of charges. Yeah. That one's kind of oriented weird. So you're going to have a whole lot of attraction between these molecules as a result. And water and HF and ammonia have very interesting properties as a result of this attraction between them. As a result, water has a much higher melting point and a much higher boiling point than you would predict based on its size. Really, these are all dipole molecules. They're polar molecules. You should see dipole attraction. So dipole, we said, increases with size. But when you actually plot out the boiling points of these three substances, you're going to find that the HF, H2O, and ammonia all have much higher melting and boiling points than you would actually expect based on their size. And then one last little thing to keep in mind, as temperatures decrease, hydrogen bonding actually increases to a certain point. You've probably heard that water is densest at 4 degrees Celsius, which is sometimes why our lakes turn over. The water at the surface gets cold, it ends up being denser and sinks to the bottom, forcing a turnover of the lakes. But then it starts to go the other direction again, which is why solid water or ice actually floats on the surface of water. And that's a good thing, because if it didn't, as the cool air freezes the top layer of the water, it would sink to the bottom, and this would continue all winter long until ponds, lakes, everything would freeze solid. So the ice actually helps to insulate the water from freezing, and as a result, we can still have fish in the spring. We probably all know that Lake Erie, the surface of Lake Erie, tends to freeze almost completely throughout the course of the winter months, which is good for those people in the south towns that always get lake effect snow. But Lake Ontario being deeper and having a lot more motion of the water, it doesn't typically freeze. So that's why we're seeing lake effect snow off of Lake Ontario these days. All right, let's go to the next page. The van der Waals forces are actually the last of the forces of attraction we're going to talk about that involve only covalently bonded substances. And van der Waals forces, which you can kind of lump in with something we call London dispersion. So I'm just going to write that above here, London dispersion. If you go on to take AP Chem or Freshman Chem, they may talk about the difference between the two, but we can kind of lump it in together. This is a very weak force of attraction, so I'm going to write that down. It's weak, but it does exist, and the reason why it's weak is because it occurs in nonpolar molecules. So these would be all of our nonpolar molecules, those that are diatomic or those that the charges cancel out based on their symmetry. So we're going to pretend these are two atoms of a noble gas. We'll say these are xenon. So in xenon, there's a nucleus somewhere in there, but it's shielded by all these electrons on the outside. And what happens is the electrons are always moving around. Okay, I think we talked about this earlier in the year. There's really no way to say exactly where an electron is at any given time because they're constantly moving. And what'll happen is, for whatever reason, they may kind of randomly end up all on one side, kind of exposing all the protons on the inside of the atom. And as a result, the neighboring atom will be attracted. All of those electrons will be attracted then to the exposed nucleus, and then the other side will have the nucleus exposed, and so on. This is really, really momentary, which is why it's really weak. And we call it a momentary electrostatic attraction. This one also increases with size. And this is why group 17, or halogens, you see all three phases of matter in that group. Group 17, that would be fluorine, chlorine, bromine, iodine. So as you go down that group, fluorine and chlorine are gases. They're smaller atoms, smaller molecules, so the forces of attraction aren't as great. But when you get to bromine, then it's great enough that the molecules are attracted enough to each other to become liquids. And then when you get to iodine, now it's much stronger as a result of the size of the iodine molecules, and it's a solid. So that's why you see all three phases of matter in group 17, or the halogens. All right, the last thing we're going to talk about is molecule ion attraction. And this one, technically it's not a force of attraction because it's not just happening between molecules, it's happening between molecules and ions. But essentially it occurs when ionic substances dissolve in water. All right, so what this picture is supposed to be showing you, this is the lattice work of an ionic substance you guys know as table salt, sodium chloride. So you have your sodium ion attracted to your chlorine ion, which is attracted to a sodium. So as a result, you get this beautiful crystalline structure. But when you put it in water, because of the highly polar nature of water, so it has the positive end and the negative end of the molecule, it actually comes over and it'll pull off the ions. It'll orient itself in such a way that it'll pull off the ions. So over here in this corner, you see you have the negative end and the positive end oriented like this because it's going to pull off this sodium ion. Where this one, we have our positive end oriented toward the chlorine ion, the negative end over here. And now you can see here's actually a sodium ion that's already been removed, and each of the water molecules is oriented so that the negative end is toward that positive sodium ion. So you may be asked to actually draw what this would look like on the exam, and what this would look like, you would need to show each of the ions of your ionic substance, okay? And then you need to show the water molecules actually oriented properly. So since sodium is positive, the negative side of the water molecules will be oriented toward it, which would be the oxygen side of the molecule. So if you recall, it looks like this, but we're going to get into drawing what we call particle diagrams shortly, and we're going to depict these atoms as little circles. So water is a bent molecule, and I want to orient my oxygen atom toward my sodium atom because that's going to be the negative side. So this is my oxygen, and these are my hydrogens. Here's the oxygen, here are the hydrogens. I just twisted it so that the oxygen side was aimed toward that positive sodium ion. And you need to draw at least 3 water molecules around each of the ions so it's obvious that you know the proper orientation of the water molecule. Now with the chlorine, we're going to need to spin the water molecule around so that the hydrogen side of the water molecule is oriented toward the chlorine ion. Now, if you wanted to, you could actually fill in what the elements are, or you could fill in the charge, so you could put the O's and the H's in your diagram, or you could even label them with their charges. My suggestion is that you probably shouldn't do that, because what I see students do is orient them properly and then label them wrong. So if they hadn't labeled them, they would have gotten the credit, but because they labeled them incorrectly, they didn't get the credit. So I suggest that you don't label them, but I wanted to show you that that is a possibility. All right, so what does all of this mean? Well, these forces of attraction actually hold molecules closer to each other. So the stronger the force of attraction is, it'll probably be a solid versus a liquid, which is a little weaker force of attraction, versus a gas, which is very little attraction between the molecules. So if I were to say to you, I have a substance that is a solid, you would be able to then predict that the forces of attraction in that substance were relatively strong, versus a gas, which the forces of attraction would be relatively weak. Or we could take it in the other direction, and if I gave you a list of different dipole attraction or polar molecules, you could look at their size and predict their relative melting and boiling points with each other. I hope this makes sense, but we're going to do some activities in class. Please do come in with questions and make sure you tried your best in answering the questions in this video.